This is an introduction to a paper called Graph Articulation in Architecture. And my name is Samson Adjei, and the paper is submitted as part of the Students and Staff Conference at London Metropolitan University 2022. The idea and context of this paper, as a kind of short abstract, is it would like to consider or reconsider the level of reduction inherent in graph notation diagrams and consider how we might extend graph expression of architectural plans through closer articulation. This would serve as both a reflective device and a more compatible format for architectural applications of machine learning. Principal methods include study of existing literature and experimentation. To begin with, to kind of give a sense of context, graph notation, as is formally defined today, has a history in mathematics, tracing back to Leonhard Euler, a Swiss mathematician, also known as a geographer, physicist, astronomer, logician, and engineer. The foundation of graph theory is believed to have been inspired by a puzzle considered by the citizens of Königsberg, pictured here, now known as Kaliningrad. They would regularly cross the 7 bridges connecting 2 islands, Napehof and Lomps, defined by the Pregel River. They asked themselves often if it's possible to visit each ground, but with the condition of each bridge being crossed only once, and were unable to reach a conclusion. This prompted the mayor of Danzig to write to Euler, 960 kilometers away in St. Petersburg, for help. Though reluctant, Euler entertained the problem, but soon concluded that it would not be possible to cross all bridges once only. In doing so, he realized for this question, the topography of the ground was irrelevant, and devised a new form of reductive notation, translating, in this case, ground to nodes and bridges to links, which enabled a clear perspective on the question, on the problem, which is illustrated here. Areas of land A, B, C, and D are translated into nodes, also known as vertices in the language of graph theory. And then the bridges here are translated into edges, also known as links. This new abstracted reduced diagram refers specifically to the relationships between in this case, the patches of land. And it was through this method and then further kind of interrogation of this diagram that Euler was able to reach his sort of logical conclusion. This language of notation predates Euler by some time. In turning our attention from the ground of Königsberg to the night sky, we find a much earlier point and line description of the stars. Of these, the Don Juan Chart, star chart, stands as the oldest known astronomical map of the complete northern hemisphere. We see here in this partial cropping that again, this language of the point and the line as a way of describing relationships and associations is something that has spanned across time and practices. Unlike the isomorphic elastic principles of Euler's graph, the Don Juan chart contains a topographic translation of the stars' relative positions. Though instrumentally, the Don Juan chart is not intended to form a basis for mathematical operations. It serves instead to support the astrological predictions as outlined by its accompanying text. Today, this notational language of the point and the line is more familiar, or perhaps familiar to many in various guises. Here we have a detail of the London Underground map designed by Henry Charles Beck in 1931, and it hasn't changed so much since then. Returning again briefly to Euler's charts. So unlike the Cartesian graph that everyone's familiar with, which has an x and a y coordinate, the connected graphs of Euler can be rearranged in various forms. You can turn it upside down, you can reorient it, you can reconnect it, and these three variations of Euler's graph notation are considered equal. We can see that despite the different arrangements of nodes and the different formations and shapes made by the links, the critical connections remain the same. The number and nature of the relationships as well is consistent. This is also true for this graph theoretical representation of the serotonin molecule as an example of another form of graph notation that's common and familiar to those involved in chemistry. And then also, more recently, graph notation has become familiar to many in the social sciences and also those in data analytics. Here we have an example of a social network analysis of a plane known as Les Miserables. Here we see the relationships between individual characters of the play, and through observation or through observing the graph, we can see the relationships between groupings or families, associations between friends, and so forth. Moving towards architecture, we find that other forms of graph, here we have an example of a justified graph, have been made popular and familiar through research practices by organizations such as Space Syntax. Here we have an example of an architectural floor plan on the right-hand side with a justified graph which explores the adjacent relationships between spaces, which here in this example each space is converted, or each space is considered as a node, and the thresholds between them become links. A further example, this is from Stanislaw Chala's paper, Architecture as a Graph, a computational approach. Here, Chila is introducing the idea of the graph as a form of mediating device which can be more readily adapted to and interacted with by and through computing. And here too, we're in an example of a moment from a design process. We have a graph produced by an architect, simply by hand, who is considering relationships, possible relationships and plausible relationships between programmatic elements. You can imagine that this diagram will inform the development of an architectural design. Returning to this idea of articulation, this paper would like to consider this idea of the graph and its isomorphic state allows for reinterpretation. So in this instance, someone perhaps unfamiliar with the original plan, but only presented with a graph, might consider alternative or other ways of re-expressing or redeveloping a floor plan, reinterpreting a floor plan from the graph. However, one issue is presented in that because links and edges only address associations, direct associations between programmatic elements, they're in this state unable to distinguish between the thresholds of doorways or other forms of portal and open plan situations or scenarios where two programs, where one space might share two programs, or conversely where two programs might be divided more explicitly through a doorway. Here we have a second interpretation or reinterpretation of the graph. Orientation in architectural plans becomes a significant factor. In this instance, the previously isomorphic graph has been transformed so that the relationships remain the same, and all of the room functions remain present. However, the bedrooms have been moved to the north, and the plan essentially inverted across the kind of horizontal axis, thereby creating, in this instance, north-facing rooms. So even though this graph is the same as a previous example of the two-bed floor plan, this is much less desirable interpretation given the solar orientation of these rooms. And this anchoring of solar orientation is not typically present in graph interpretations of floor plans. And so returning to the floor plan, this study would like to introduce the idea of a slightly higher order of articulation regarding south-facing light and or other directions of light as necessary. For example, artist studios might prefer north-facing light. This thereby introduces a contextual element to the graph, where previous examples have typically addressed the plan as an isolated object. The second and equally significant form of articulation addresses the envelope, in particular windows. The windows help to mediate and also importantly indicate the envelope. Just as significantly as the entrance node, the window nodes work together to help signify the extent or boundary edge of a connected architectural graph. Within the graph, the third level of articulation centers on thresholds, introducing the idea of the node to represent more directly different forms of threshold between programmatic elements. In this example, doors in particular are highlighted by their own nodes. This in turn helps to differentiate between a room that has shared functions or multiple functions and rooms that have individual functions. Together, these three levels of articulation bring the connected graph closer towards the plan, whilst still retaining a degree of its isomorphic flexibility and potential for reinterpretation. A fourth or an optional fourth and final level of articulation additionally considers interior furniture. In this instance, each room has its own graphlet or subgraph relating to objects of furniture or fitted items that help to define the use or meaning of a room. An advantage of this level of articulation, especially in terms of computational interpretations such as machine learning, especially in terms of computational analysis, we might find that recognizing small group arrangements of items of furniture within a restricted vocabulary is a more effective way of understanding or defining a room function than simply a single word term. So in this example, for the living room, we recognize the TV, coffee table, sofa, side table, and so on. An advantage of this method is that different types of living room can be expressed through the addition or subtraction of furniture elements, and different configurations can start to or begin to introduce different nuances of space or program that are less direct or otherwise difficult to express through single word terms. Previous and more conventional forms of computing have developed and have a lot in common with the history of the Cartesian graph, with its more familiar x-y coordinates. More recently, we have developments in machine learning, which takes a very different approach to more conventional ideas of logic. As such, much with the development and histories of notation that have emerged in one discipline and been adapted by others, this paper is curious to see what could happen if and where other creative disciplines were to explore the possibilities of connected graph notation as an additional form of expression.